All right, today is all about the good, bad, and ugly of Euler's method. And first, you want to answer the question, why is Euler a good method? So why is Euler a good method? And we'll define what good means in that context. And in particular, why does it give you a good approximation of your solution? Give you a good approximation, a good approximation, very squishy approximation of your solution. What? And in order to do this, we have to define and talk about the concept of error. But I just want to remind you, in Euler's method, there are really two quantities at play. Because on the one hand, we have our approximations, right? What we called y0, y1, y2, etc. Our approximations. y0, y1, y2, up to y capital N. But on the other hand, we also have the actual values of your solution. Because if you have a solution y, you can actually evaluate them at all the points. So the values. And I'll show it to you in a picture of our actual solution. Solution y, which is really y at t0, y at t1, up to y at t. And in particular, it makes sense to compare the two. So once again, let me draw a little picture of what's at stake here. So let's say you have your solution y. Maybe look something like that. This is y, your true solution. And then you have all those points, t0, t1, t2, t3. Maybe that's tn. Then the two quantities that are at play are your Euler's method points. Maybe this is y0, which has to be the initial condition, and maybe that's y1, y2, and then maybe y of tn. Oh no, sorry, yn. Maybe like this, like this. But also, as I said, you can actually evaluate y at our points. So for instance, y of tn is here. But then we have the initial condition, y of t0, y of t1, y of t2, etc., etc. This, maybe this. And in particular, notice between each of those points, there is a distance, because maybe not the first one, but between y of 1 and y of tn, there's a distance here, y2, yt2, here, and then here the distance is very big, here and here and here, which tells you sort of how Euler's method deviates from the true solution. And what is the error? The error, we just define it as the length of the biggest stick here. So we have all those green sticks, all those green distances, and the error is the biggest distance, which in this picture would be here. That's what we call the error. So let me define it and then interpret it. The definition of error. So it depends on your step size. It depends on how small your step is. So we call it E of H. And again, it's the length of the biggest stick. So it's the maximum of all those distances. So y naught minus y of t naught, which technically is 0, y1 minus y of t1, up to yn and y of tn minus y tn. And again, in that picture, it's just the biggest possible distance between our actual solution and the Euler's method points. So again, in this picture is the length of this green line here. Now, really, you have to think of the error as the worst possible scenario. In the sense that if one of those Euler's points deviates a lot from the solution, then the error is big. Like, for instance, in this picture, once again, most of the points are close to the true solution, but because this blue point is far from the solution, the error is big. Conversely, if the error is small, it means all the Euler points are close to the true solution. So if E of H is small, then all the YK, that's the definition of this maximum, the YK are close to YTK. So think of a situation like this, where you have maybe your true solution and then your actual values, and all the Euler points are close to your actual value. Might be here, here. See, that would be small error, versus big error means even one of the points is far. And so what do we want? Well, ideally, of course, you want the error to be small, at least for a small step size. So ideally, we want the error to be small. Small, that is. At least, I mean, we don't really care about large step sizes. Really, generally, if H is small. H is small. That is, in terms of the word you love, limit, we want the limit as H goes to 0 of E of H to be 0. And that's really the definition for us of a good method. Namely, if the step size is small enough, then the error is small, meaning all your points are close to the true solution. Sort of like what we've seen in the previous example, where the function was close to the graph, or like the Euler points were close to the graph. And the good news is, in fact, Euler's method is a good method in the sense that this error is small. So fact, for Euler's method, technically there is some constant C, such that not just for small h, but for all h, we have E of H is squeezed between minus CH and CH. In other words, the error is less than or equal to C times H. And in particular, I will mention the proof, by the way. In particular, this does imply by the squeeze theorem that E of H goes to 0. limit h goes to 0 of E of h is 0, and therefore Euler is a good method. A good method. Meaning eventually all the points actually go towards a true solution, which is good. And just a quick word about the proof. So there's some details in the notes, but essentially it follows from two things. So follows from, of course, the formula of Euler's method, ytn plus 1. Again, the future is the present plus the ODE, f of y and tn, but also from a Taylor expansion. From a Taylor expansion. Expansion, meaning, for instance, in general, f of x plus h. So also the future is the present plus derivative and maybe some terms with h squared. So if you look in the notes, you actually see that there is a h squared term, but because you do it multiple times, you have to divide it by h, and then you do get that the error is less than or equal to ch. All right, that was the good side of Euler, and now we will see the bad side in a future video.